All right, so in this drawing that you copied down, basically there's two things going on. The curve is rising as you go from the point a f of a to the point a plus dx, f of a plus dx. So you can see the curve actually jumped. We call that delta f. And to find the gap, the rise here in black, you would simply find the y value, f of a plus dx, and the y value, f of a, and subtract them. Okay? But the tangent line at a has only risen a little bit less, see, between a and a plus dx. So see where the blue is here? This is your tangent line. And the tangent line also has had its own rise in this interval dx. But it's not as much. It didn't rise as much as the curve did. So this little red segment here, that distance is called df, not delta f, df. And that can be calculated by simply multiplying the slope of the line times the run, right? So you might be looking at this and saying, I don't understand that thing. What is that? Well, remember that slope is always rise over run. So what you see here in red, this formula in red, is really just like writing rise is slope times run. Right? Rise is slope times run. The slope of this blue line is f prime at a. That's the slope of that blue line. Dx is the amount of run, so this is just slope times run. F prime at a times dx. F prime at a times dx. All right? And this we call df. df. Some people call the estimated change. It is not the true change in the function, right? The true change in the function is delta f up here. This is the true change. The amount the function actually jumped by. So the blue line, again, is trying to estimate the amount of change that the curve actually made. Okay? If you can find delta f, that's always more accurate than finding df. But df has meaning as shown in this diagram. Okay, I thought we'd just do a couple of problems where we find true change, estimated change, and then we'll also find the difference between those to see how big this little green gap is right here. See this little green gap? This right here is called the approximation error. That little green gap. It's just basically delta f minus df, just like the formula says on the left. And we'll also do absolute value for that because it's supposed to be like an error and you don't give a negative error. All right? It's just absolute error stuff. All right, let's go on, assuming you have the picture. If not, you can finish drawing it tonight from your worksheet into your notes. Okay, let's just try an example where we'll start really simple. Let's say that the function is x squared, a is simply 1, dx is 0.1, and we're trying to find those three things: true change, estimated change, and approximation error. Now tonight you do not have to draw a picture unless you feel it's helpful. So this one's actually a pretty simple picture. It's just x squared like that. All right, except I can't draw very well with a stylus yet. And if you go out here to 1 and 1.1, which is dx says 0.1, so we're talking about 1 and then 1.1, which is right next to it, right? We have this tangent line, and we basically have the amount that the tangent line has risen between 1 and 1.1, and the amount that the curve has risen between 1 and 1.1, which is clearly a different amount. They both rose by a different amount. Okay, so true change is just basically going to be f of 1.1 minus f of 1. So that's 1.1 squared minus 1 squared, which is 0.21. Okay, so hang on to that answer. That's one of your three answers there. Estimated change has more to do with the tangent lines. We actually don't even use that. We're not going to use that. We're going to use the tangent line at 1. Okay, so why don't we find the equation of that tangent line right there. So the tangent line, we're now calling it L of x, as you remember. It's supposed to be f prime at a times x minus a plus f of a, right? This is the function x squared, so the derivative is 2x. So this is just going to be 2a times x minus a plus a squared, basically. And we are at a equals 1, right? So this is going to be L at 1. It's 2 times x minus 1 plus 1. This is like your tangent line. To find the estimated change, you can just kind of abbreviate it all by doing this. df is supposed to be f prime at a times dx, as it says on the board, right? So you could just go like this, 2a times dx. A is 1, it's given in the problem. dx is also given in the problem. It's 0.1. So the estimated change is 0.20. The approximation error is just the difference between your red answer and your black answer. So basically you're just going to do 0.21 minus 0.20 absolute value. So the answer is 0.01. I'm going to color code everything. You've got your black segment in the picture. That's this vertical one. This is delta F. The little red one right here, that's df. And the green one, there is your estimated error. Estimation error, approximation error. So it's basically black, red, green. Black, red, green. Okay, you do not have to draw a picture. You can just follow the formulas. We also have the equation of the tangent line. I don't even know why I found that now that I look at it. Down there in blue. Didn't really use it much at all. Just reminding myself, I guess, of how to do yesterday's problems. Let's go on and look at the statement we wrote in red just a moment ago. Okay? Let's talk about this for just 1 second. I'm only doing that one example for you, okay? My estimated change on that last problem was when I did the red calculation right here. Right here, see? I have df equals 2a dx. I just want to look at that with you real quick. Does this remind you of df dx equals 2a? Looks kind of like that, right? It just looks like it's been cross-multiplied. See that? Are we allowed to cross-multiply derivatives? So this is the question that was asked for a long time. Are we allowed to cross-multiply something like this? df dx equals 5. Can I just multiply both sides by dx? Can I just write df equals 5 dx? Man, that's really iffy. Remember, the df dx is not really a fraction. It really means, what it really means is limo f of x plus h minus f of x all over h equals 5. Who gives us the right to multiply both sides by h? We wouldn't do that, would we? No way. Right? It's buried in the limit. Why would you be feeling like you multiply that over if you can't, right? But that's exactly what this means. So it turns out that you actually can do it. You actually can multiply the dx over. But the question is why? You know, we understand the idea that rise is slope times run. But we're talking about a derivative here, you know. I can understand if we had a triangle like this, you know, and you wanted to say, oh yeah, that's dx, and this is like your df, you know, and df is basically the slope times dx. That's just basically rise over run in disguise. But listen, we're doing a tangent line. There's no triangle. Okay, we're zooming in on a specific point, infinitely close. I understand if you wanted to call this like delta, you know, if you wanted to call this like delta f right here, and call this delta x, and say something like delta f equals m times delta x. Let me rewrite that a little bit scribbly. You know, that would make sense. But all of this has been shrunk down to 0 size and made into the, leaving this notation, df equals f prime at a dx. Let me just say this about this argument. We are allowed to do it, and it's because the chain rule has sort of convinced us that we can treat our df dx and dg dx and du dx as fractions when they really are not fractions. The chain rule allows us to treat them that way. So we will start doing this, guys. We're going to start taking the dx and moving it to the other side. So in all the derivatives you're asked to do tonight, it'll say find the differential. That just means take the derivative and put the dx on the right. Throw the dx on the other side.
On this worksheet, are we given like f?
You'll be given f, you'll be given a, you'll be given dx.
Okay.
I'll record a couple more examples for you in case you didn't follow everything there on that last part. Okay, so let's just talk for a second longer about that last few comments we made there. So we know that if you have a function like f of z equal to x squared, we know that df dx is equal to 2x. But what we're saying today is that we can also write this now as df equals 2x dx. Or if you had something like f is equal to 5 times x, df dx, of course, is just 5. But we can write this now as df is equal to 5 dx. So we're moving the dx over, you could say. This is called the differential for x squared. This is called the derivative for x squared. They are slightly different. This is differential, IAL, there at the end. And this down here, of course, is the derivative of 5x. And this is the differential for 5x. So what exactly is a differential? Well, differential is a non-zero small value of change. How small? Infinitesimally small. So for a long time this was under debate. How can something be infinitesimally small but yet not be zero? And looking at this example here, how can df really be 5 times larger than dx if both of them are infinitesimally small changes? How can anything be infinitesimally small yet 5 times larger than something else that's infinitesimally small? What does this all mean? Well, it turns out, like I said before, that it doesn't really matter what it means so much. All that matters is that this is possible and doable, and it's because of the chain rule that we're allowed to separate our df and our dx in this way. So we're going to treat them like separate ideas, df and dx. And notice that df is 5 times larger than dx is. But don't worry too much about what they mean geometrically. We just need to get familiar with having df and dx separated. You could even solve this and put dx is 1/5 df if you like. We will need these sorts of substitutions in our next chapter on anti-differentiation.